Right, welcome back to our 7th video of our Regents Chemistry installment as we review the entire year in a very quick and concise way with the goal of just hitting the main topics from the units that we have covered or you have covered in your classroom. The next one here is going to be intermolecular forces and gases. Now, sometimes these are split up into different units, but they are so closely attached that we might as well use them together. So let's start with intermolecular forces, or IMFs. And what they are the attractive forces between molecules. Attractive. Oh, boy. I thought today would be nice because there's no students in school. The network should be running pretty quickly, but I guess not. So attractive forces between molecules. Now, the goal here, or the main point here, is that molecules of the same kind are attracted to one another. They're not bonded to one another. Their interaction of positive and negative parts is what draws them either closer together or doesn't draw them closer together, and therefore they end up further apart. Each of the different types of molecules will have different strengths of intermolecular forces, and they will have different names for the type of intermolecular forces they are. But before we get into the details of it, we'll talk big picture here. And if a substance has weak intermolecular forces, the molecules are not attracted to one another. They're not repelling each other necessarily, but they're just not attracted to one another. What happens is they spread apart. And typically, substances with weak intermolecular forces are gases. And because they are gases or liquids, we can also conclude that weak intermolecular forces will have low melting points and low boiling points. Those two things come together hand in hand. And we can also generally say gas, right? But on the flip side, if something has strong intermolecular forces, oh boy, strong intermolecular forces, what we're going to be dealing with is high melting points and boiling points. Right, and so these typically be your solids or your liquids, mostly solids. And the molecules of this type, they're strong because they are very attracted to one another. So they stick closer together, and if you remember anything about what we've talked in the past, molecules that are close to one another tend to represent solids. Right? And why are they close together? Because they're attracted to one another. And molecules that are farther apart tend to be gases. And why are they gases? Because they're not so attracted to one another. Right? Obviously, temperature plays a factor in here too. More temperature, more energy. But generally speaking, when you're talking STP, the intermolecular force can really be determined, the strength of the intermolecular force, by the phase of matter that substance has. Okay, so that's kind of a quick general overview. Now, if we wanted to get into the nitty-gritty of the chemicals behind it, which we're going to do, the strength of the intermolecular force will depend on the size of the molecule, right? Larger molecules have stronger intermolecular forces. And it also will be determined by what we like to refer to as the END. Okay? END, which is the electronegativity difference. So if a molecule is made up of, let's just say, HF, I believe we would be dealing with a 2.2 and a 4.0, 2.2 and a 4.0 electronegativity. That difference, right? The difference, we'll take it absolute value difference, just so we don't get too crazy, is 1.8. And that's a very high electronegativity difference. That molecule is going to have strong intermolecular forces. This is can also be shown on the flip side if we're just talking covalent molecules with CH bonds. CH bonds are a 2.4 and a 2.2, or 2.6, excuse me, and a 2.2. So the END here comes out to be 0.4, much smaller, much weaker intermolecular force when you zoom out from the bond. Okay, so electronegativity difference plays a big role in this. We kind of already mentioned this, but we'll say it again. Bigger molecules have stronger intermolecular forces. And the reason is there's more bonds in these molecules. And because there are more bonds in these molecules, there are more positive and negative electronegativity differences. And it just allows for more attractive sites to other molecules. It's a network of positive and negative parts of a bond connecting, drawing into one another. That's what we're dealing with. So more bonds will lead to a stronger intermolecular force. Atoms in a molecule that have larger electronegativity differences, larger ENDs, these keep coming out like P's, are going to have stronger IMFs, right? So I kind of already talked about both of those things. Bigger differences in electronegativity, stronger IMFs. And that really comes down to the fact that if we go back to polar molecules and polar bonds, for instance, in this example that I was explaining, fluorine has a very high electronegativity. So even though it's sharing its electrons with the hydrogen, the electrons are pulled in the direction of fluorine more often and they're more frequently. And what this ends up creating, back to polar molecules, is very strong positives and very strong negatives. But in a nonpolar bond where it's much more evenly shared, right? Yes, because carbon has a stronger electronegativity, it pulls the electrons. But it's a weaker negative pole and a weaker positive pole. So they'll still influence others, but it just won't have the same effect. The three types of bonding, the three types of intermolecular forces in order of strongest to weakest are hydrogen bonding intermolecular forces are the strongest. And this only happens if hydrogen is bonded to an N, an O, or an F. Those are the only three cases that we have to worry about hydrogen bonding. So if a molecule has any of those bonds somewhere in it, it's going to have hydrogen bonding. I know we haven't talked about organic chemistry, but alcohols have an OH group. They possess hydrogen bonding. Amines and amides have NH bonds. They're going to have hydrogen bonding in their molecules. Okay. Dipole is the next strongest. It's weaker. It really has to do with any type of polar molecule. A polar molecule, wow, that came out really bad, sorry. Polar molecule will have dipole, so long as it doesn't have N, O, and F. But in reality, hydrogen bonding is just a strong version of dipole. So there's no difference on how those two things work. It's just that specifically hydrogen bonding are those three bonds. And then van der Waals, 4 regions chemistry is what we use to describe nonpolar. molecules. And that's how we rank our covalent intermolecular forces. Into gases now. Gases have the most entropy. The most entropy. And the word entropy means randomness and disorder, really. But, you know, if you think about it, gas molecules that are filling the room that you are in right now, or maybe you're outside, those gas molecules can go anywhere. They could start in the corner of the room and end up in the hallway. They could end up outside, and eventually they do. So the path of a gas molecule is very disordered and very random. But a solid doesn't do that. I mean, if you look around and you find something solid near you, the phone that you're holding or the computer that you're holding, the molecules that make up that computer, they're not going anywhere unless you move the laptop or the phone, right? They are stuck in the place that they are, and that is a very ordered phase of matter. The kinetic molecular theory. Okay, so this is a big one that we talk about in my classroom. In that it's a big one because we don't memorize a lot of things in Regents chemistry because a lot of it is practical application. But the kinetic molecular theory of ideal gases has a few rules to it. Not rules, guidelines, I guess you would say. And it's that a molecule is behaving ideally, meaning how we want it to, if they are moving in a constant straight line motion. Right? So when molecules are moving in a constant straight line random motion, that's one thing. Gas molecules don't do this. You have to understand that. Everything that I'm about to explain right now is not what actually is not reality. It's how we would want them to behave. Gas molecules in reality move much more like this, but we can't predict that. Mathematically and chemically, we can predict things close to perfect if we assume that. We also assume that they have the molecules themselves have no volume. If we assume that the molecules have no volume, we can make calculations a lot easier. Again, not a factual statement. Everything that's made up of matter has volume, but we pretend for the kinetic molecular theory that there is no volume. And we assume no attractive forces. So no IMFs. Again, not true. Even van der Waals nonpolar molecules have some sort of attraction to one another. But we are making these assumptions to pretend that we can perfectly predict what gases are going to do. And there is actually one more. So it's 1, 2, 3, and the fourth one being elastic collisions. And what that's really referring to, what that means, what an elastic collision means, is that no energy is lost over the course of a collision. And the Regents will sometimes get tricky with this question because it will say in an answer, which one of these goes for the kinetic molecular theory? The answer might say, collisions result in no transfer of energy. And that's an incorrect answer. Because two gas molecules can collide, according to this theory. They can collide and transfer energy from one to the other. But an elastic collision means that the total amount of energy stays the same. So energy can be transferred, but it won't be lost. It may be lost from one molecule to the next, but the net energy that those two molecules started with would stay the same. Right? This would be like saying you have two cars driving at two particular speeds with X amount of energy. If those two cars collided, according to the kinetic molecular theory, one car may stop, but the other car would be going at double the speed or double the velocity it was going at to begin. And we just know that that's not the case, because when two cars crash, they transfer all of their energy into one another, and they lose all of the energy in that collision. Okay, so the kinetic molecular theory is the set of conditions we pretend are true in order for us to predict gas laws. Now, the gas law part of this year is one of the easier ones. Okay, so let's get into the math, which we don't really have to talk too much about because it's all on your reference table. All right, so the one thing that we need to note about the kinetic molecular theory of ideal gases is if we take any gas and give it a high temperature and a low pressure, any gas will behave as close to this as possible. Okay? High temperature, low pressure. Now, when it comes to gases, there are three things that we use at Regents Chem level that can influence the behavior of a gas. And those three things are temperature, pressure, and volume. Okay? Pressure, temperature, and volume. All of those things will influence one another. And if we hold one thing constant, we can predict how one variable will affect the other. So, temperature and volume, if pressure is constant, are directly related. Direct. If temperature goes up, volume goes up. And it's easy to understand why. Temperature is the speed of the molecules. If the molecules move faster, they're going to spread out. They're going to push the walls of a container out because they have more velocity. And therefore, their volume will increase. Pressure and volume. Okay? Pressure and volume are indirectly related. They're indirectly related. And they're indirectly related, it's kind of, again, easy to understand. If you're increasing the pressure on a gas, what you're doing is you're pushing in on it, right? That's what pressure is. It's a force. Increasing pressure would be an inward force. Squeeze a balloon, it gets smaller. Let go of that balloon, it gets bigger. That's pressure and volume and how they affect gases. Temperature and pressure would be the last relationship. This being assuming volume is constant. Temperature is speed. If the molecules are moving faster, they are going to create more pressure. Right? It's the difference between walking into a wall and running into a wall. The wall is going to feel a lot more force, a lot more pressure, if you're moving at a high speed. So this as well is a direct relationship. And if no variable is held constant, volume or anything can be determined using the combined gas law on the back page of the reference table. And just as a reminder, that math looks like P1 V1 over T1 is equal to P2 V2 over T2. So I hope that gave you a nice little overview on gases and intermolecular forces. I think we went a little bit more in depth on this one than we normally do, but that only benefits you. So please, if this helped or if you enjoyed it at all, hit the like button, subscribe to the channel, and I will catch you in the next video. Thank you.